In this video, we're going to look at the beginnings of 6.3 exponential functions. These are functions that take the form f of x equals c times a to the x, and these are called exponential functions because the variable is in the exponent. C would be a number, a would be a number, but x would be our variable. So the domain of an exponential function is all real numbers. So that variable, that power, can be any real number. A has to be a positive number, and a cannot be the number 1. That's the only positive number it cannot be. And c is just some constant. It can be anything but c except 0, because then this whole thing would just be 0. Okay, so one of the things you'll be doing and with exponential functions is solving exponential equations, and you'll also be graphing. So in this section, I just want to show you some simple exponential equations that are introduced in 6.3. When you get to 6.6, there'll be more complicated ones. But in 6.3, we have some simple ones. And they use this idea that if a to the u is equal to a to the v, these are both, notice this is like our a to the x, then if this is true, then u is just equal to v. And recall our variable is going to be in the exponent. So if we could just get rid of it out of the exponent like this, then it'll be very easy to solve. So this is a technique we'll use on some of the simple equations. So for example, here's one. Our first example would be e. We have a base of e. E is a mathematical constant. It's a it occurs naturally in the world, just like pi. You're familiar with pi. We use the symbol pi because the number is irrational and the digits go on forever without repeating. So e is the same way. It's a base of 2.14, etc., etc. I don't have all those digits memorized. You can find it on your calculator if you raise e to the first power. It's on your calculator. But it can be a base because it's a number that's greater than 0 and it's not 1. So if e to the 2x power is equal to e to the 5x minus 9 power, then we know we're supposed to find x. But if this is true, then we can just say, well, then 2x is equal to 5x minus 9, and just solve this simple linear equation. Subtract 5x, negative 3x equals negative 9, divide both sides by negative 3, and of course x equals 3. So we solved this exponential equation. Our solution set is 3, and indeed we could go back and plug that in to check. We could say e to the 2 times 3 is equal to e to the 5 times 3 minus 9. So that's e to the 6 is equal to e to the 15 minus 9. E to the 6 equals e to the 6. So it checks. You can always check these by plugging in your solutions in where x was. Okay, that one was already set up, same base on both sides. But what if it's not? We might see one that looks a little bit different. So my second example here is 2 to the 5x minus 2 equals 8. So we don't have the same base on each side, and the idea would be to try and write both sides with the same base. Using your calculator, a lot of times you're going to want to get your calculator and just play around for a minute and see what power perhaps can I raise 2 to get 8. Is that possible? And yes, it is. 2 to the 5x minus 2, I would say, is equal to 2 cubed, because 8 is 2 cubed. Now I have my a to the u equals a to the v, so u equals v. And now I solve for x. My solution set is 1, and again, you can check that. Plugging in 1, 5 times 1 is 5, 5 minus 2 is 3, 2 to the third is 8. It does check. So that's one technique for solving exponential equations. That's the technique you'll use in the 6.3 solving section. In the next video, I'm going to go over graphing exponential equations using transformations.